This lesson is the 6.03 Review Stoichiometry and preparing for the 6.03 quiz. Lesson 3, Review Stoichiometry. Review concepts presented in the lesson stoichiometry and its uses and mole-number relationships. In this lesson, you will review what stoichiometry is, how it is used, various ways to express amounts of ingredients and products, and the mole. You will also review Avogadro's number, which remember is how much? 6.022 times 10 to the 23rd, and how it can be used to convert numbers of atoms or molecules to mass. Goals for this lesson: demonstrate mastery of important knowledge in the relationships from lessons of stoichiometry and its uses and mole number relationships. I strongly suggest clicking on the student guide and using that to help you take your notes in this section. It also has a few other links that you will need. Key concepts in stoichiometry and its uses. In chemical reactions, elements combine in whole number ratios to form compounds. Remember, you cannot have half of an atom. You have to have the entire atom. Mass is conserved in chemical reactions, meaning the amount you start with is the same as the amount you end with. Balanced chemical equations are written expressions of chemical reactions. Using balanced equations, stoichiometry, first of all, shows numerical relationships between the reactants and products, such as how many atoms are on each side, the mass on each side, and it helps predict the quantities on either side of the reaction. Quantities of reactants and products can be expressed in many ways, such as atoms, molecules, mass, volumes, and moles. So again, stoichiometry is based upon the law of multiple proportions, meaning whole numbers, where amounts are measured in many ways, including atoms, molecules, mass, and volume. Key concepts in mole number relationships. So let's look at the diagram first this time. The mole can be expressed as 6.022 times 10 to the 23rd. It's also called Avogadro's number, and it allows conversions between the number of particles and the mass. Chemists use the mole as a unit for counting atoms or molecules. The mole is defined as the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. Avogadro's number, or N sub A, is the number of atoms, molecules, formula units, or things in 1 mole. And again, 6.022 times 10 to the 23rd items of anything per mole. Just like there's always 12 in a dozen. 12 eggs in a dozen, 12 cats in a dozen, it doesn't matter. 12 is always how many there are in a dozen. 6.022 times 10 to the 23rd is always how many there are in a mole. Depending on the substance, the mass of 1 mole is equal to the atomic, molecular, or formula mass of the substance expressed in grams. In other words, the 12 grams here of carbon-12, meaning that there's 12 grams in 1 mole. So you can look at the periodic table to find that is true for other elements. And the mole is the basis for stoichiometry and is used in determining the amounts of products or reactants. So organize the key concepts you have studied. So we have stoichiometry is based upon the law of multiple proportions, where amounts are measured as atoms, volume, and what else? Molecules, moles, number of particles, or 6.022 times 10 to the 23rd. So if you're not sure where to go, I would say, ooh, I know this number. What is that number? Well, let's look at my other choices. Expressed as Avogadro's or this. So, okay, I know that's Avogadro's number. And Avogadro's number in 6.022 times 10 to the 23rd describes which of these? The mole. And moles and Avogadro's numbers convert between mass and number of particles, and therefore the other thing that's measured with law of multiple proportions is molecules. Now look at some model problems and complete the problem set. Turn to page 45, Stoichiometry and its uses, in the Chemistry Problems and Solutions book, doing problems number 1 and 2. It is very important that you do those when it tells you to. So, again, you scroll up and you find Problems and Solutions, a lab guide. And when this loads up, here's the lab guide and here's the problems and solutions. So you're going to click here and it's going to take you to your book. Now you're going to have to type in the page number. So if you've been doing these, you have an idea of where you're at, and we're actually going to be on page 98. So we're on page 98, which is what we're going to go over next. Problem set 45, Stoichiometry and its uses. Objectives: define stoichiometry and demonstrate the law of multiple proportions in formulas. Stoichiometry helps chemists quantify the amounts of reactants and products in chemical reactions. In other words, tell how much you start with and how much you end with. Stoichiometry is the branch of chemistry that deals with quantifying the amounts of substances that are involved in reactions. Stoichiometry is important because chemicals react in specific ways. A reaction will proceed to completion only if the reactants are present in the correct ratio. In other words, we've been talking a lot about chemical reactions and you've predicted a lot in the lab, but what we haven't really mentioned is that they only happen if you have enough of all the reactants. Just like if you try and bake a cake without eggs, you're not going to get a cake. It's just going to sit there and boil until it burns in your oven. Okay, so it's the same idea in chemistry. You need the correct amount of all your reactants or stuff to make the chemical reaction happen. If there is not enough of one reactant, the other reactants will not be completely consumed. Using stoichiometry, chemists can predict the amount of a substance that will be produced in a reaction. They can also use stoichiometry to predict whether a given reactant will be completely consumed during a chemical reaction. So that's basically a fancy way of saying, let's say you're making a batch of cookies and you have a dozen eggs. Well, do you need to use a whole dozen to make one batch of cookies? No. So you're going to have leftover eggs. It's the same idea. Sometimes you have leftover chemicals if you don't have enough of the other chemical to produce the correct reaction. Stoichiometry relies on a rule called law of multiple proportions. This law states that elements can combine only in specific ratios of whole integers or whole numbers. For example, hydrogen and oxygen can combine to make water and hydrogen peroxide, so they can make H2O or H2O2. But they cannot combine to form H3O4 or H1.5O2.3. Okay, so these should be obvious that they can't because they're decimals. This one is just that they occur in certain combinations based on how badly they want electrons. The subscripts on the atoms in a chemical formula give the number of atoms of each element in one molecule or formula unit of the compound. Remember, the law of multiple proportions. The law of multiple proportions states that elements can combine only in specific ratios of whole integers. In other words, when we put hydrogen and oxygen together, you can get H2O or H2O2, and that's it. In chemical formulas, such as H2O, subscripts represent the numbers of each type of atom in a molecule or formula unit. So when we have H2O, how many H's are there? 2. And how many O's? 1. The subscript 1 is never used in chemical formulas. It's just like math class. You just write X, you do not write 1X. If only one atom of an element is present in a molecule or formula unit, that element's chemical symbol has no subscript in the chemical formula. So like H2O, we do not write H2O1. We just know that there's 1 there. All right, so let's look at example 1. Quantify the ratios of compounds in elements. Quantify the ratios of elements in compounds. Silver nitrate, or in other words, AgNO3, is a white solid that can stain skin brown, is sometimes used for temporary tattoos. How many atoms of silver, nitrogen, and oxygen will be required to form one formula unit or one molecule of silver nitrate? All right, so we're looking at our subscripts. AG, there's no subscript, so how many are there? There's just one. N, there's no subscript, so how many N's are there in one formula unit or one molecule? There's just one. O3, so how many oxygens have to be present in this molecule or formula unit? 3. Example 2. Identify proportions in reactants. So let's look at the tip first. If one of the reactants in a reaction is completely consumed or used up, but the other reactants are not completely consumed, so you have left over, like I talked about having leftover eggs when you bake cookies, the reactant that is completely consumed is called the limiting reactant. In example 2, chlorine is the limiting reactant. So maybe you want to make 2 batches of cookies. Well, we have a dozen eggs, we have plenty of eggs, but let's say you only have 1 stick of butter, well, you can only make 1 batch then. So even though you have plenty of eggs, you can only make 1 batch of cookies because you're limited based on how much butter you have. So your butter is your limiting ingredient or your limiting reactant. All right, let's look over the example. Identify proportions in reactions. Table salt, or sodium chloride, NaCl, can be produced by reacting sodium metal, Na, with chlorine gas, Cl2, as shown in the equation below. 2 NAs have to come together. Remember, the coefficient means there's 2 copies of it. 2 NAs plus 1 molecule of Cl2, so it's 1 copy of 2 chlorine atoms glued together, yields 2 copies of NaCl. If 100 atoms of sodium react with 48 molecules of chlorine gas, Cl2, how many formula units of NaCl will be produced? Okay, I switched screens because the first time you read a question like that, you might feel a little overwhelmed. So we're going to talk it through with our easier example. And it says, I need to make a bunch of cakes. Each cake needs 3 eggs and 1 stick of butter. I have 4 sticks of butter and 10 eggs. How many cakes can I make? All right, so 1 butter plus 3 eggs equals 1 cake. So now I can look at how much of everything I have. So if I have 4 butters, how many cakes can I make? I can make 4 because for every 1 butter, I make 1 cake. So 4 butters, 4 cakes. How many eggs do I need? Well, if 1 cake takes 3 eggs and I want to make 4 cakes, 4 times 3 is 12. I need 12 eggs. Can I make 4 cakes? Well, I only have 10 eggs, so no, I can't. I can't make 4 cakes. So my eggs are my limiting reactant. All right, so instead, I have 3 butters, 9 eggs, and I can make 3 cakes. So I'm going to have leftover, but that's okay. In fact, I'll have 1 egg left over, but, well, I can't make part of a cake. So I have to use 3 butters, 9 eggs to make 3 cakes. So again, this is like our law of multiple proportions. I have to use whole numbers, and my proportion is for every 1 butter, I have 3 eggs to make 1 cake. So it's 1 to 3 to 1, so 3 to 9 to 3. So if I reduce, I get back my original proportion of 1 to 3 to 1. All right, so now let's look at one with chemicals in it. So I'm going to look over my example again right here. And it asks me how many I will have. And actually, I'm going to stop the recording because I'm going to run out of time, and we will start here with the next recording.